Hello everyone. In this video, we'll discuss some examples of equivalence relation. So, let L be the set of all lines in a plane, and R be the relation on L defined as L1, L2, such that L1 is perpendicular to L2. So, mainly the question is one L1 line is there. Okay, this is a line L1. So, another line is there L2. Okay, so if they are perpendicular to each other, this L1, this line and this line are perpendicular to each other, then we can write L1, comma L2 belongs to R. This is our definition of the relation, which is defined this lines defined in a plane. Okay, in 2D plane. Okay, now I assume these three lines L1, L2 and L3, okay, in a plane. So any line, the line itself is not perpendicular to itself, right? So any line L1 is not perpendicular to L1. This line is not perpendicular to itself, so that's why L1, L1 is not belongs to R. Now similarly symmetric L1, belongs to L1, L2 belongs to R. That means L1 is perpendicular to L2. From here we can conclude that L2 is also perpendicular to L1. That's why we can write L2, L1 belongs to R. Now for transitivity, let L1, L2 belongs to R and L2, L3 belongs to R. That means L1 is perpendicular to L2 and L2, this L2 line is again perpendicular to L3. L1 is perpendicular to L2, first condition. The second condition is L2 is perpendicular to L3. This is the third line. So from here we can see in the diagram that actually L1 is parallel to L3. That's why we can write L1, L3 not belongs to R. Okay. So hence R is symmetric, right? This is symmetric, but neither reflexive nor transitivity. Okay. Next. So next example is the set similar the set all lines in a plane and R be the relation L defined as L1 is parallel to L2, right? So if their lines are parallel, we can write this one is our L1, this is another line L2 and this is another line L3 because they are dealing with parallel line. Now come here. We have to show that R is a equivalence relation. So I am considering this three line. So any line L1 is parallel to L1. This line itself is parallel to itself, right? So ultimately we can write L1, L2 belongs to R. Now symmetric. L1 is parallel to L2. L1 is parallel to L2. So similarly L2 is also parallel to L1. So ultimately we can write L2, L1 belongs to R. Now transitive. L1 is parallel to L2 and L2 is parallel to L3. Ultimately we can say L1, L3 belongs to R because L1 and L3 is also parallel to each other. So L1, L3 belongs to R. So from here we can conclude that this relation R it satisfies all the conditions of reflexivity, asymmetry and transitivity. So ultimately we can say R is a equivalence relation. Now example number 3. Show that the relation R in the set of integers given by R is equals to order pair A comma B such that B divides A minus B, or you can say A minus B is a multiple of 4. This means same. Moreover, another is there. Sometimes they used to write like this: A equivalence of B modulo or mod 4. Okay, this all three mean same. Now let us consider three elements A, B, C belongs to the integer set. Okay, then by the definition A minus B is a multiple of 4. If it is a multiple of 4, we can write A minus B is equals to 4k, k be any integer. Now let us check for the reflexivity. We know A minus A is equals to 0. Why I am writing this one? Because I have to show A comma A belongs to this R element. So we know A minus A is equals to 0, and 0 can be written as 4 into 0. So ultimately A minus A is a multiple of 4, and here A minus B is a multiple of 4. If it is a multiple of 4, then A comma B belongs to R. Similarly, A minus A is a multiple of 4. That's why A comma A belongs to R. So we have the reflexivity, right? So next, let's check out for symmetry. What we have? We have A comma B belongs to R. One way to show B comma A belongs to R. That means B minus A is a multiple of 4. So A comma B belongs to R implies A minus B is equals to 4k by the definition of the relation. And if we multiply this one with minus, so ultimately we'll have B minus A is equals to 4 into minus k, right? And this minus k is also again an integer, right? If minus 2 is an integer, then 2 is also integer. So ultimately we have B minus A is a multiple of 4, right? If it is a multiple of 4, then B comma A belongs to R. Then from here we can say that R is a symmetric relation. How? A comma B belongs to R, then we have B comma A belongs to R. Next, transitive. Let A comma B belongs to R and B comma C belongs to R. So once we have A comma B belongs to R, B comma C belongs to R, we have to show this A comma C belongs to R. A comma C means we have to show A minus C is a multiple of some number, say multiple of 4. Okay, so here A minus B is belongs to R. This implies A minus B is equals to 4k1. K1 is integer here, and this comes from the definition of the R. Similarly, B minus C is equals to 4k. Now as I have to get A minus C, if we add this one and this one, ultimately B cancel out, right? So we'll have A minus C. That's why we are adding these two. And here we have 4k1 plus 4k2. 4k1, 4k2, if we take 4 common, ultimately we have that k plus 1 also again an integer, right? Say 4s is an integer. So from here we can say that A minus C is a multiple of 4. If A minus C is a multiple of 4, that means A comma C belongs to R. We assume A comma B and B comma C belongs to R, and ultimately we have A comma C belongs to R. From here we can say that R is transitive, right? If R is transitive, R is symmetric, and R is reflexive, then R is an equivalence relation, right? So here R is an equivalence relation. Thank you.